Let us continue with Chapter 2 on power semiconductor devices used in power converters. The history of power electronics began with the introduction of mercury arc rectifiers in 19th, then vacuum tube rectifiers before the World War II, and finally the power electronics age began in 1948 with the invention of the silicon transistor at Bell Telephone Laboratories. Whereas the mercury arc rectifiers or metal tank rectifiers provide AC to DC conversion, power converters in power electronics can operate either to convert AC to DC, DC to AC, AC to another form of AC, or DC to DC. So various topologies can be obtained using power semiconductor devices. So what are these devices? The first one invented was the PN-PN triggering transistor. So it is called as thyristor or silicon controlled rectifier, abbreviated by SCR. In 1958, the first commercial thyristor was developed by the General Electric Company, and this was the beginning of a new area of power electronics. And since then, many different types of power semiconductor devices and conversion techniques have been introduced. The various types of power semiconductor devices developed since 1970s can be classified broadly in 5 types. Power diodes first, then thyristors, which have different types: silicon controlled rectifier, gate turn-off thyristor, or integrated gate commutated thyristor, MOS controlled thyristor, which was not commercialized. Power bipolar transistors, BJTs, which are dioing devices in power electronics. MOS field effect transistors, MOSFETs, insulated gate bipolar transistors, which combine the advantages of BJTs and MOSFETs into one single device called IGBT. So we will consider all of these types of power semiconductors, their area, their use in power converters, the operating areas, and so on. The motivation for using switching devices in a power converter is to increase the conversion efficiency. An ideal power semiconductor switch has zero conduction voltage drop during on state, zero leakage current at off condition, and turns on and off instantaneously during switching. Such a device is lossless with a converter efficiency going to 100%. But in practice, practical power switches, power transistors or thyristors, have some limitations. They can block only a finite voltage during turn-off, a finite current flow, and appreciable voltage drop during turn-on. They require finite time to reach maximum voltage and current during switching, during turning on and off. And in general, voltage-driven devices like IGBTs and MOSFETs require small power for triggering into conduction, whereas some other types require substantial amount of current during turn-off. So we will consider all these characteristics. Power semiconductor devices, switching devices can be operated as switches by applying control signals to the gate terminal of thyristors and power MOSFETs and to the base of bipolar transistors. Designers can choose power semiconductor devices from a wide range of voltage and current handling capabilities, looking to the data sheets, to the commercially available ones, as well as from a range of operating and switching characteristics to find the one best for a given application. So when you will choose a semiconductor device, a power semiconductor device, you will need to know the following parameters. The forward blocking voltage required by the device. So how much voltage how much voltage will your semiconductor device be subject during operation in the off state. So with a safety margin, you should choose the VDRM value. Reverse blocking voltage. How much reverse blocking voltage will it see? Maximum single package current, mean and RMS on-state currents as well. So according to these current ratings, you should choose again. Maximum operating frequency. The unidirectional or bidirectional current capability. Will you require in your application current flow in both directions or only in a single direction? So this will affect the choice of the required power semiconductor. The switching times, switching requirements at turn on and turn off. The maximum operating temperature, Tmax, we will see that power semiconductor devices should be cooled by means of heat sinks. Otherwise, the junction's temperature will increase beyond the safe value and the device may burn out. Forward voltage drop during conduction, like the forward voltage of a diode, all the other power semiconductor devices have forward voltage drops during conduction. And also dV by dt, di by dt ranges are important. Otherwise, breakdown may occur because of exceeding the ratings. So let us see the power semiconductor device capabilities now. A comparison of the most widely used ones. The thyristor, power BJT, MOSFET, here power MOSFET, GTO, gate turn-off thyristor, the insulated gate bipolar thyristor, and the integrated gate commutated thyristor. These are the major devices. The availability, starting from early 60s up to late 90s, these are developed and commercially became available. The technology, the state of technology is mature for most of them. Voltage ratings in the order of 5 kilovolts for thyristor. So they can withstand in the off state 5 kilovolt voltage without breakdown. This is quite a high value. BJT is only 1000 volt. MOSFETs typically 500, but there are MOSFETs which reach 1000 volts nowadays as well with a small current rating. 5 kilovolt for the gate turn-off thyristor, 3.3 kilovolt for the IGBT, which has now reached again 6 kilovolt level, and the IGCT about 6 kilovolts. Similarly, the current ratings are seen here. But these current ratings are the absolute maximum values and are not related to the voltage ratings. For example, it is hard to find a 500 volt MOSFET which has 200 amp RMS current rating. But rather than this, a 100 volt MOSFET may have 200 amp RMS current rating. So these are the maximum you can find commercially. As you see, the lowest one is the MOSFET, whereas the highest ones are the thyristors. Either gate turn-off or integrated gate commutated or silicon controlled rectifier type of thyristors have all high current ratings, high current and voltage ratings. But despite this, the switching frequency of thyristor-based power semiconductors are low. This is a 50 Hz device. So switching frequency not available means that it operates only from AC line of 50 or 60 Hz frequency. And in general for AC to DC conversion. The BJT can go up to a few kilohertz, the MOSFET up to megahertz. GTO is a higher frequency device as compared to the thyristor, similarly the IGCT. And IGBTs can go 100 kilohertz is a very limited value actually, a few tens of kilohertz frequency. So it is mostly a medium power, medium frequency device, IGBT, whereas MOSFET is a high frequency, low power device. And thyristor family is a high power but low frequency range. The gate drive circuits, simple for thyristors, very difficult for gate turn-off type of thyristors, and difficult for BJT, but very simple for voltage-driven devices. So this is a general comparison about device capabilities, and you see here a summary of these capabilities in a three-dimensional graph, where the voltage rating is on y-axis, 5, 4, 3, 2, and 1 kV, and the x-axis is the current rating up to 3000 amperes, whereas the frequency rating is starting from 1 kHz, 1, 10, 100, and 1 MHz in logarithmic scale. The backward area here belongs to thyristors. Thyristors are very low frequency but high operating voltage and current devices. In the medium range, which is shown by the hatched portion here now, is the IGBT, this range. It started with a small region here, but it has expanded up to the one shown by the hatched portion. In the highest frequency range is the power MOSFET, but it is the lowest voltage and current rating device, so lowest power capability at the same time. You can classify these switching devices based on their operating characteristics as follows. For the diode, it is an uncontrolled turn-on and turn-off device. As you all know, if the diode is forward biased, with the bias exceeding the threshold voltage, the diode turns on without any control signal being applied. Controlled turn-on but uncontrolled turn-off device is the silicon-controlled rectifier. The general name given to thyristor. Thyristor is the general name, but silicon-controlled rectifier is the special device used. It can be turned on in a controlled manner, but there is no control on the turn-off, as we will explain later on. Controlled turn-on and off characteristics for all transistor family devices plus the gate turn-off thyristor device. So power BJT, power MOSFET, or IGBT can be controlled during turn-on and off. Pulse gate requirements for the silicon-controlled rectifier or GTO, continuous gate requirements for the transistor family devices. In order to keep the transistor in on state or in off state, you need to apply a continuous gate pulse. Bipolar voltage withstand capability for the silicon-controlled rectifier. In the off state, it can withstand both positive and negative voltage across its terminals. Unipolar voltage withstand capability are for the transistor family devices and for GTO type of devices mostly. Transistor devices are not capable of blocking considerable negative voltage. So you should take care of this in your design, in your converter application. Bidirectional current carrying capability is for the triac. Triac can be one single device or back-to-back connected SCRs also form a triac. Unidirectional current capability, here there is a change. The power MOSFET must be bidirectional current carrying capability. Please correct this in your slides. Unidirectional current carrying capability devices are SCR, GTO, BJT, IGBT, and diode. Why MOSFET is a bidirectional current carrying capability device? Because it has an intrinsic diode, a built-in reverse diode across its terminals between drain and source, as we will see again in the preceding slides. So these are the characteristics and symbols of power semiconductor devices. First of all, the diode. As you all know, it has an anode-cathode voltage VAK, the anode and the cathode terminals. Current flows from anode to cathode when the device is forward biased. So ID versus drain current versus anode-cathode characteristics. It has such a rising curve in the first quadrant, but in the third quadrant, a reverse breakdown occurs beyond the rating of the device. So if the diode voltage rating is exceeded, reverse breakdown occurs, and this phenomenon will also be explained in the following slides. Thyristor is in some way a controlled version of the diode. Diode's controlled version means a pulse is applied between gate and cathode. A current pulse between gate and cathode is used to turn on the device, which is forward biased. Again, forward bias is necessary, but also the instant at which turn on starts depend upon the instant at which the gate current is applied. So that's again the characteristic, and we will see how gate triggering affects the anode current versus anode cathode voltage characteristics. Gate turn-off types have a symbol with two bars here, arrows up and down, as you see, to show that it can be turned off via gate current. So this is a very special type of application, very special type of power semiconductor, only used in very, very high power applications. Let us continue with triac power semiconductor, which can be considered as two back-to-back connected thyristors. Again, the triac is put into conduction by applying a gate current with respect to one of the terminals, and it can be triggered into conduction in both directions. IA can be positive or negative, as it is seen from the characteristics of IV plane in the first and third quadrants. Light activated SCR is another type of silicon controlled rectifier, which can be triggered into conduction by illuminating the gate region. So this kind of power semiconductors are for very high power applications in the order of several megawatts range. Now the BJT, NPN or PNP BJT, can also be configured to operate in power converters. It has again a collector, emitter and base terminal, and it is triggered into conduction. It is put into conduction by applying a base current. Usually Darlington pairs are used here in a chip, more than one transistors cascaded, so as to obtain high current ratings at the output. So this is the collector current versus collector emitter voltage characteristic for the power BJT, where base current is a parameter. Note that in power electronics, power semiconductors are operated as high frequency switches. That is, they do not operate in the linear region, but only in the cutoff and saturation region. So this is here the operating region in the on state and in the off state. So this part is not used in power converters, in power electronics, because of a very high power dissipation, lowering the efficiency and increasing the temperatures of the devices. So either fully on or fully off states of power semiconductors are used. Let us skip IGBT now and consider the N-channel power MOSFET. That's the symbol of the power MOSFET, the gate, drain and source. When you apply a voltage pulse between gate and source, you can start conduction of drain current. And the channel opens here. We will see the physical construction of this device later on. The drain current against drain to source voltage with gate to source voltage as a parameter is seen here. So here again, the operating region is the constant resistance region here during on state, and during off state for VGS equals to 0 or negative values, the drain current is very small, negligibly small. Now, there are some disadvantages of both of these devices. The RDS-on, the drain-to-source on-state resistance, limits the ratings of N-channel MOSFETs. And power BJTs are subject to some undesirable features such as secondary breakdown, high base current requirement, and complexity of the base drive circuit, especially in the powerful devices. And so an idea came to combine the two, BJT and power MOSFET, in order to obtain an insulated gate bipolar transistor. Here, the input is like the MOSFET, a gate emitter voltage control signal puts the device into conduction, but once in conduction, the current flows through the collector emitter as if it were a BJT. So the conduction characteristics, the output characteristics are very similar to BJT, whereas the input characteristic, that is the control characteristics, very similar to the power MOSFET. So the corresponding device is called insulated gate bipolar transistor, and it has the characteristics of IC against the collector emitter with gate emitter voltage as a parameter. So we will consider all of these, most of these at least, power semiconductor device properties in this second chapter. Let us start with the power diode. You all know the symbol for the diode. In the ideal case, it is off when reverse biased. When the anode cathode voltage is negative, it is off. It is on when it is forward biased. This is the IV characteristic for the ideal diode. Various general purpose diodes are available for power applications, either discrete packages, screw mounted packages, stud mounted packages, disc types. So as the size increases, as you see, you go from smaller packages to bigger in size packages. These are called disc packages. They have base surface areas quite high, and hence can be cooled down via heat sinks easily for high power applications. So these are for thousands of amperes. These are for hundreds of amperes, for tens of amperes, and for amperes. The diode packages are available commercially. Also transistor-like packages like TO220, TO247, and so on. For Schottky rectifiers, a special kind of diode, which is a metal to silicon barrier, very fast switching speed can be reached, and these are packaged in transistor-like packages of TO220 case, for example, and two diodes in one chip will give you a rectifier configuration, as we will see later on. Now in practice, the symbol and the IV characteristics are shown here. In practice, we have a certain forward voltage drop during conduction, which increases exponentially with the diode current, with the anode current flowing through the diode. In the reverse bias state, the diode is in off condition, in off state, but very small leakage current in the order of microamps will flow through practical diodes. And beyond the reverse voltage withstand rating, VRRM, which I have talked about in the first chapter, the junctions break down irrecoverably, and the device goes into a short circuit case, into a short circuit failure case. So in more detail here, the forward voltage drop during forward conduction state, which is in the first quadrant of the IV plane, the leakage current in the third quadrant, here is the reverse blocking state, Here is the forward conduction state, but beyond a certain reverse voltage, reverse breakdown occurs, as I stated. Now, how does a PN junction diode operate now? In a PN junction diode, silicon material is doped either with P-type or N-type impurities. In an N-type material, formed from either phosphorus, antimony, or arsenic, where atoms have a free electron in their outer orbit, form an N-type region, whereas in the P-type material, there is a lack of electron, that is a free hole at the outer orbit, like in the case of boron. So the silicon material doped with P and N-type materials are brought together in a junction. So they make a PN junction. When such a junction is reverse biased, that is, the P-type material negatively biased, whereas the N-type material is positively biased. So the free electrons on the N side are attracted towards the positive bias, whereas the holes towards the negative bias, forming at the central region a depletion region free of carriers. So there is here a diffusion of N materials towards P and holes towards N region, forming a plus minus potential drop at this depletion region. Hence, an electric field is formed here. So this is the reverse bias, non-conducting or off state of the power diode. What about the forward biased power diode? When a positive bias is applied to the P region, whereas negative bias to the N region, now holes are pushed away to the N region, whereas electrons towards the P region in the opposite direction. So the holes in the N region at this side here form minority carriers. There is a minority carrier injection to the N region from P region, and this minority carriers start conducting current through the power diode. So that's what I have explained just now. One point to note here is that as the reverse voltage applied to the PN junction diode, that is minus plus reverse bias, the increase in the reverse voltage magnitude will cause a widening of the transition region here, depleted of carriers. So as this region is widened further, if you increase the applied reverse voltage magnitude, at a certain point, the depletion region reaches the terminals shown by hatched parts here. So when terminals are reached, a short circuit occurs, and this is the reverse breakdown case. So the negatively biased diode becomes shorted when the depletion region reaches the terminals. So this is the reverse voltage rating of the power diode. We talked about this. So these are the regions, therefore, forward conduction, reverse blocking, say, and reverse breakdown parts. What about the switching waveforms now? When a diode switches from on to off condition while carrying a certain current, the current starts to drop. It does not cease here, but it continues in the reverse direction until a certain amount of charge is recovered at the junction. So this is the reverse recovery charge here, and it's magnitude and duration depends upon the device characteristics and the on-state current of the device before turning off. So when switched from forward to reverse bias, it continues to conduct due to minority carriers in the PN junction, which require a finite time called reverse recovery time to recombine with the opposite charges and neutralize. Now, why do we talk about these details? Because this reverse recovery charge causes switching losses within the device, and hence power diodes are different from small signal diodes in that sense. They must withstand, without overheating, the losses at the operating frequencies and at the operating voltages and currents. So there are three types of diodes, power diodes: general purpose diodes, high-speed diodes or fast recovery, ultra-fast recovery types, and Schottky diodes. So these are used in power electronics applications. The general purpose ones are used in line frequency rectification applications. That is, from 50 or 60 Hz AC line, you take the voltage and you rectify it by means of general purpose diodes. They have low on-state voltage drop, but large reverse recovery time. They are available up to several thousands of volts and several thousands of amperes. From 6,000 volts to 4,000 amperes, general purpose diodes are available. What about the high-speed diodes now? For the high-frequency operation, with lower ratings than the general purpose ones, but they have very low reverse recovery times, depending on the diode type, of a few hundred or few tens of nanoseconds to a few microseconds. They are essential for the high-frequency switching power converters, DC to AC, DC to DC converters especially. What about Schottky diodes? Schottky diodes have very low on-state voltage drops, 0.3 volts nearly. They have very small recovery time, typically no recovery time actually, in the nanosecond range, because Schottky diodes are not PN junctions. So there is no minority carriers, there is no charge recovery at the junction. This is just the silicon to metal barrier. Limited blocking voltage for these diodes, unfortunately, for the silicon types. Silicon carbide types are now being introduced with higher ratings. So these are some commercially available fast recovery, ultra fast recovery, and Schottky rectifier types from various companies. And you see here the maximum voltage ratings, average current ratings, forward voltage values, typical values, and reverse recovery times. As reverse recovery time increases, switching losses during reverse recovery increases. So the diode is the device you are all familiar with. Now let us continue with silicon controlled rectifier. In some version, like a controlled diode. But it is different from a diode. It is a PN junction device. So within this chip, you have many parallel such constructions, PN type, where the equivalent circuit and the symbol are represented here. The diode with a control voltage taken from the cathode here, the gate to cathode current will trigger into conduction a forward biased thyristor. We said this is a PN device. It is constituted actually of two intrinsic BJTs. You can consider it as if it were two cascaded BJTs, Q1 and Q2, an NPN transistor in cascade with a PNP transistor. How does it operate? When you apply the gate signal, this transistor, NPN transistor, turns on, causing base current flow in the PNP transistor, and it turns on this transistor as well. So therefore, there is a current flow from anode to cathode during conduction. These are the corresponding VI or IV characteristics, anode current versus anode cathode voltage characteristic for a thyristor. If no gate current is applied, anode current can flow only after a breakover voltage is reached. If you apply sufficiently high gate current, then a diode-like first quadrant operation, that is forward conduction mode, can be obtained. In the reverse blocking region, you have similar characteristic to the diode. It is a latching device. We will see what does this mean. It is a minority carrier device again, because minority carriers injected from P to N regions will cause the device to conduct. Double injection because of PN layers leads to very low on-state resistance and very low forward voltage drop, even in very high voltage devices. So it cannot be actively turned off. This is a disadvantage of the device, but a voltage bidirectional two-quadrant switch can be obtained by using a thyristor, because it has forward and reverse voltage blocking capabilities both. So these are the voltage and current ratings of the devices. Similar to the diode packages, you have either discrete types or you have stud mounted types, you have disc packages, screw mounted types for thyristors. So as we said, the thyristor structure consists of 4 layers of power semiconductor material of alternate conductivity type, PN. So 3 junctions are formed, J1, J2, and J3. Here is the anode terminal, cathode terminal, and gate terminal. So whenever you inject a current through the PN junction device here, actually you turn on the thyristor, and hence anode current is latched. Otherwise, it remains in blocking state. So anode cathode are the same terminals as in the diode case, but you have a third conduct, the gate case, the gate terminal, which is a control electrode, normally inside the P region. The thyristor is a trigger into conduction device, turned on by a positive gate current pulse, but once it is on, a negative pulse cannot turn it off. They can be subdivided into different types. Line commutated thyristor, which we will consider mostly within the scope of this course, but in very high power applications, gate turn-off thyristor, which is nowadays replaced by integrated gate commutated thyristor, and some other versions which have been worked in the laboratory, say. Light activated SCR is also a physically commercial device, but for very, very high power applications, it is an expensive device. So we said that the thyristor turns on when the anode cathode voltage is positive and the positive gate current is applied. In a forward biased thyristor, once in conduction, the anode current is said to be latched. So what is latching? This means that current flows continuously even if gate current is removed. So it is out of control now. It controls itself. So the intrinsic gates in the parallel operating thyristors within the chip are triggered with the previously conducting thyristor, so that they do not cease conduction. In the forward biased mode, if no gate current is present, a small leakage current flows, and this is the forward blocking region. Both forward blocking and reverse blocking regions are available for the thyristor, means that forward biased or reverse bias that are not sufficient to trigger into conduction the device. There must be a gate current to start the conduction. If the forward breakover voltage is exceeded, on the other hand, SCR may trigger into conduction, but this is not a normal way to trigger the device into conduction. It is not desirable to reach the breakover voltage each time the thyristor is to be triggered. The presence of a gate current, even small, reduces the breakover voltage magnitude. If sufficiently high breakover voltage is applied, then the thyristor can start conduction like the diode. We said that the thyristor cannot be turned off by applying a negative gate current. It can be turned off if the anode current goes to 0 then or towards negative values. This happens when negative portion of a sine wave occurs in 50 Hz applications. Typically, when voltage ceases, the current through the device also reduces towards 0, and hence the thyristor turns off. This is called line commutation. Another method of turning off is forced commutation, that is, the anode current is diverted to another circuitry, which is rarely used nowadays. So that's why thyristors are mainly used for line commutation applications, and especially in line commutated rectifier applications. As I said before, when peak reverse voltage is exceeded, avalanche breakdown occurs and large destructive failure occurs. This is an irrecoverable case of the semiconductor. So that's the typical IV characteristics of a thyristor. The reverse blocking region with reverse leakage current and reverse breakdown, very similar to the diode case. In the forward region, forward conducting region, if a sufficiently high gate current is applied, the thyristor can start conduction like a diode. But otherwise, if no gate current is applied, breakover voltage must be reached, so near the ratings of the device. And as gate current is increased, this breakover voltage is reduced. So that's the forward conducting region for the thyristor. There are two important currents here, the latching current and the holding current. Usually holding current is about 1/2 of latching current. Latching current is the amount of current required to put the device into conduction, even when the gate current is removed. So the device is latched and does not cease conduction. Holding current is the amount of current to be reached in order to stop conduction in a thyristor which has been latched previously. So the basic operating regions of the thyristor are shown here in the IV plane, the anode current versus anode cathode voltage region plane. So there are three regions: region A, region B, and region C. According to the junctions, when anode cathode voltage is negative in region A, junctions J1 and J3 are reverse biased, whereas the central junction is forward biased. So as reverse voltage magnitude is increased, the width of the depletion layers increase, and beyond a certain point, breakdown. There exists 4 methods in switching an SCR from region B to region C. Remember that region B is the forward blocking region. So this is the region here. Beyond this point, forward conduction starts in region C. So how to switch from region B to region C? First, as the forward voltage is increased, the depletion layer at junction J2, central junction, increases proportionally, and some minority carriers cross junction J2, thus dislodging more and more minority carriers, resulting in avalanche breakdown in the junctions. Then junctions J1, J2 and J3 become all forward biased. This is the critical anode cathode voltage which switches the device from region B to C, known as forward breakover voltage. So if plus minus the voltage exceeds a certain limit, even without gate excitation, you will have forward conduction initiated. But this is not a desirable way of turning on a silicon controlled rectifier. It damages the device in the long term. If some minority carriers are injected into the gate region, the device can be switched from region B to C, which is the normal gated operation. As you see here, if the gate is triggered, if gate current is further increased, you will obtain a diode-like forward conduction characteristics. This is the desirable normal gated operation. The device can be switched into conduction by a rapid change of anode-cathode forward voltage. This is dV by dt turn on due to the capacitances between anode gate and gate cathode. So the time required to switch from region B to C is in the order of a few microseconds. Again, this is an undesirable way of switching the device into on state. Some special types of thyristors have the property of conduction by illuminating the gate cathode junction. So this is a way of firing the device in light activated SCRs, which are very powerful devices used in the industry. Let us have a look to the terminology. A silicon controlled rectifier is a unidirectional current capability device. It can carry current from anode to cathode only, not in the reverse direction. And it is turned on by a positive gate current pulse when forward biased. So this is the way of normally operating the thyristor. The forward blocking voltage and reverse blocking voltage are important quantities. The highest positive voltage across the device, at which the device will be still blocking the flow of current when not turned on without gate excitation, is called VGRM, the maximum repetitive voltage applied in the forward polarity between anode and cathode. The reverse blocking voltage is the highest negative voltage across the device, at which the device still blocks the flow of current in the reverse direction without breakdown. Here gate is ineffective, of course. Thyristors turn on very fast, in the order of microseconds, and the time is limited by the rate of rise of anode current di by dt. The thyristor, when forward biased, as we said, can be switched into on state by injecting current to the gate terminal relative to the negative cathode. Once the device has been switched into a low impedance state, it remains in this state until anode current has been reduced below the holding value. So otherwise it cannot be turned off. And once the anode current has exceeded the latching level, the gate current can cease. You can stop the gate current, and the thyristor remains in the on state irrespective of the conditions of the gate circuit. So this is a latching device. In order for the thyristor to attain and retain the on state, the anode current must reach its latching level and must not fall below the holding level. Let us consider a single thyristor as several individual cells in parallel. That is, PN junctions are in parallel. So once you apply the gate cathode pulse and you trigger the first thyristor into on state, this anode current will supply the gate current of the nearby thyristor, which will push it into conduction. Similarly for the rest. So that's why once the anode current has reached a certain level, it cannot be stopped. The latching current is typically double the holding current, but both are being much less than 1% of the full load value. Now let us have a look to the turn-on characteristics of the device. When a gate current is applied, there is a time delay during which the anode current does not rise appreciably and the anode cathode voltage remains constant. The anode current then increases rapidly and the anode voltage falls rapidly during the rise time, TR. The anode voltage then falls relatively slowly during a spreading time until the steady state is reached. So let us see here. There is this is the gate cathode current, the anode cathode voltage during turn on, and the anode cathode current during turn on again. So the delay time where voltage remains the same but anode current has reached to its 10%. Then the rise time in which the anode current reaches its 90% of steady state, whereas the anode cathode voltage has decayed, and the spreading time here to the device where current spreads through the whole device. This turn-on behavior is important from practical viewpoint since conduction is initiated only in a small area. The rate of rise of current is limited by the permissible heating of the localized area. Thus, the I by dt is one of the ratings that must be observed for safe operation of the thyristor. Similarly, the rate of application of forward blocking voltage or dV by dt rating should be considered because a high dV by dt may misfire the thyristor, put it into conduction in an undesirable manner. There are in thyristor gating requirements. There is a considerable range of characteristics within a given production batch, and all thyristors can be assumed to have a characteristic lying between low and high resistance limits. So if this is the gate voltage, the gate current, low resistance limit, high resistance limit, and all thyristors of the same part number remain within this range. The minimum level of current and voltage required the thyristor to turn on the thyristor is a function of the junction temperature. So also minimum voltage and current limitations are available. The current into and voltage at the gate are both subject to maximum and minimum values. The product of gate voltage and current gives a power level which is a maximum to which a maximum level is set. So in other words, this is the power rating limit for the gate. Otherwise, the gate may be overheated. Minimum voltage current limits are there, and minimum and maximum resistance limits there. So the area of certain firing is in between here. So you should apply such an operating voltage and current to the gate so as to turn the device on in a safe manner. So the triggering network, a typical triggering network for the thyristor is given here. In general, a pulse transformer is used in order to isolate the thyristor device from the electronic pulse source. In the case of a fault occurring in the power circuit, this must not propagate to the sensitive electronic circuits, microcontrollers or etc., chips, other analog controllers, etc. So the pulse source is applied through a pulse transformer with current limiting resistor and voltage limiting divider to the gate terminals. If we draw a Thevenin's equivalent for this circuit, for this overall, when you look to the left of the gate cathode terminals, it is a voltage source in series with a gate resistance and the applied gate voltage Vg, gate current Ig. Typically, E is in the order of 5 to 10 volts and Ig is in the order of 0.5 to 1 amp for practical thyristors. So let us skip these parts for the gate circuit equivalent models, and let us consider an example. Here is a single thyristor circuit which supplies power to a load from a DC source. The criteria for triggering depends upon the nature of the external load, the supply voltage, and the gate current applied and which flows through gate and cathode junction. First of all, let us consider the load line of the circuit, of the electrical circuit. VAK is equal to supply voltage minus anode current times the load impedance. The load may be resistive or, in most of the cases, resistive inductive nature. Let us start with Vs equals to Vs1 in magnitude. Again, for the sake of simplicity, we assume that the source is a DC source and the gate current is 0, so there is no triggering. What is the operating point 1? So depending upon the applied source voltage, actually, the operating point 1 may be below or above the breakover voltage. So we have to draw the corresponding characteristic of the thyristor. The silicon controlled rectifier thyristor is the general name given to a family of devices, and silicon controlled rectifier is the specific device we are talking about. So this is the characteristic for Ig equal to 0 of the thyristor, the thyristor's IV characteristic. On top of it, let us draw the load line of the electrical circuit. Just note that the load line intersects in this at this point, in this point, and that point. But note that initially non-conducting thyristor intersects the characteristic at the forward blocking region and cannot regenerate because the breakover voltage is higher than this voltage at the intersection point. So the device therefore is in forward blocking state for this particular condition. Now let us inject Ig equals to Ig1. A gate current is injected, and this gate current injection causes such a change in the IV characteristics of the thyristor with a smaller breakover. Note that now the operating point changes from 1 to 2, and hence this is the negative resistance region, the regeneration region. Once this region is reached, the anode current will latch and it will flow at a value which corresponds to the intersection point between the load line and the characteristic at point 3. So point 2 is a dynamic operating point. It is not a stable operating point, and once this point is reached, the device will trigger into conduction and will start to carry the load current. So operating point 2, which is unstable, therefore the thyristor switches into conduction state. New operating point 3 is stable. The gate current now may be removed and the conduction will be maintained at point 3 because this point corresponds to a current much higher than the latching value, which is around here. This is a zoomed view of the thyristor characteristic here, in the order of a few milliamperes or in the order of amperes, whereas in this part you are in the order of several tens or hundreds of amperes. So in order to visualize better, we have zoomed up this region. So conclusion: for the above values of Vs and Zl, gate currents greater than Ig1 can trigger the thyristor into on state. When the supply voltage is reduced to Vs2 now, after Ig is removed, what about the new operating point? We remove Ig, so the characteristic is now this one, and Vs2 is the reduced voltage applied, and the corresponding load line is this one. So as you see here, the curve slope has changed, starts to change in this region, which is an unstable region, and this corresponds to the if the current is less than the holding value, this corresponds to the operating point, which moves to the forward blocking region if current remains below holding. So thyristor will revert back to the high impedance of state. The anode current at point 4 is the holding current for the given set of conditions. Now let us increase the load's impedance. Load line becomes tangential to thyristor characteristics at point 5. If the load impedance is increased here, as you see, this is the new load line, and the operating point is reduced to point 5. Again, this is the off state, a lower value of current is obtained for the new set of conditions. If the gate current Ig1 were maintained while supply voltage was reduced to Vs3, turn off would have occurred at point 6, a lower anode current. So a higher gate current would be required to trigger the silicon controlled rectifier into conduction. So Vs3 is this one, and new characteristic that one. So again here it is in the unstable region where it reverts back to the forward blocking state. So this was a simple example to understand the operation of the thyristor. What about the requirements of firing circuits? To turn on a thyristor in the shortest time, it is desirable to have a gate current with a fast rise time up to the maximum permissible value. This rise time is best achieved by pulse techniques, where the firing circuit generates a fast rise pulse of sufficient length to allow the anode current enough time to reach the latching value. Because if the gate current duration is not enough, and then if anode current has not reached its latching value during this time period, the thyristor may revert back to the off state. What are the firing techniques applied? Either continuous gate current, usually not preferred because of the extra power dissipation. A single pulse, again not recommended because of safety. If the pulse is missed, the thyristor may miss firing into conduction. Or a pulse train, which is the most adapted procedure. A practical firing circuit will typically have a characteristic pulse with a rise time of 1 microsecond from a voltage source of 10 volts capable of delivering 1 amp. In general, reverse gate current is prevented to avoid excessive power dissipation because normally a silicon controlled rectifier cannot be turned off via negative current. So in order to guarantee the triggering of the thyristor, it is better to use a pulse train rather than one single pulse. Let us show it. For example, here the AC supply voltage and the thyristor is triggered with a pulse train as shown. After the triggering angle, called the delay angle or firing delay angle, you start to give the pulses to the thyristor to put it into conduction. So that's a typical gate current pulse of 1 microsecond rise time, 50 microsecond at least duration. You can obtain the firing circuit by this way. Let us consider an example for the latching current phenomenon. The thyristor in this figure has a latching current level of 50 milliamps and it is fired by a pulse of 50 microsecond length. You will see that this length of single pulse will not be enough or sufficient to ensure triggering of the thyristor into conduction. Show that without R, this parallel resistance here, the thyristor will fail to remain on in this circuit of RL load, where it is supplied from a DC source, and you apply a 50 microsecond pulse at a certain instant of time. Will it turn on or not is the question. So find the maximum value of R to ensure safe firing. Neglect the thyristor voltage drops. Now, without resistance R, the thyristor current will grow exponentially so that I of t is equal to a maximum current I times 1 minus e to the minus t over tau. So the first order differential equation formed by this RL circuit supplied from a DC source will give you, the solution will give you this current variation with respect to time, where I is 100 volts supply voltage divided by 20 ohm resistance 5 amps. At infinite time the current will reach 5 amp, and tau, the L over R time constant, is 25 milliseconds for the load. So substituting 50 microsecond into this equation, you will find I at the end of 50 microseconds, and this is 10 milliamperes. In that case, 50 microsecond is much less than the time constant of the load, and the initial value of the I by dt is 100 over 0.5, so giving 10 milliamperes. After 50 microsecond, the thyristor has failed to reach the latching level of 50 milliamps, and it remains a 40 milliamp of gap here between the actual current and the desired one. So the addition of a resistance in parallel will give you this extra 40 milliamp to maintain the thyristor in on state. So 100 volt divided by 40 milliamp will give you 2.5 kilo ohms. So if you put a 2.5 kilo ohm in parallel with the load, you ensure the firing of the thyristor with a single pulse of 50 microsecond in length, for a thyristor having 50 milliamp latching current, of course. What about turn-off? Turn-off behavior of silicon-controlled rectifier is the time during which the charge present in the silicon structure decays to a level near its equilibrium of state at the junctions, like in the diode actually. To turn off the thyristor, the anode current must be reduced below the holding value, and the time should elapse for the thyristor control junction to recover its blocking state before a forward voltage can again be reapplied without conduction. If the current has not dropped below holding value, then reapplication of forward voltage may cause its continued conduction, which was not desired. So typical current waveform at turn-off condition is seen here. This is the anode current. It decays with the di by dt, and it goes to negative value. A certain reverse recovery charge should be recovered during this TRR time period in order to keep the thyristor in off condition. This reverse recovery time should be elapsed. So turn-off of an SCR means that all forward conduction has ceased, and reapplication of positive voltage to the anode will not cause current flow without the application of a gate signal. Because thyristor is a latching device, remember? So this latching phenomenon makes it difficult to turn off the thyristor. There are three ways of switching off a thyristor, a silicon-controlled rectifier specifically. Natural commutation, reverse bias turn-off, and gate turn-off. Gate turn-off is a very specific silicon-controlled rectifier, specially designed rectifier, so that its IV characteristics are affected by the negative gate current, and we will talk about this later on. What about the other two? Natural commutation. From the VI characteristics of a silicon-controlled rectifier, when anode current falls below the holding value, SCR turns off. So you can achieve this in a DC circuit by opening the line switch, by increasing the load impedance, or by shunting part of the load current to a parallel circuit. Reverse bias turn-off Reverse anode to cathode voltage will tend to interrupt the anode current. So the voltage reverses every cycle, every half cycle in an AC circuit, in an AC sinusoidal source, for example, so that a thyristor in the line would be reverse biased every negative cycle and would turn off. So this is called AC line commutation or phase commutation. And mostly this commutation method is applied in the silicon controlled rectifier operation. There is also a forced commutation principle where capacitors, negatively charged capacitors are switched across the thyristor, but these are some complex circuitry. It requires complex circuitry and therefore not very much preferred nowadays. Rather than this, power transistors are employed in the case of DC to DC or DC to AC converter applications. Reverse bias turnoff is for AC to DC or rectifier applications where line commutation is naturally, line commutation occurs in the circuit. So the types of silicon controlled rectifiers are phase controlled, inverter grade, light activated, and triac types. Phase controlled types have very high voltage and current ratings with low on-state voltage drop at these device ratings. Inverter grade were formerly used in inverters and choppers, but nowadays are not employed. Light activated, triggered by a pulse of light, normally for very high power ratings, are employed in the very high power industry only. And triacs are back-to-back connected thyristors, which are used in AC voltage controller, AC to AC magnitude conversion applications. So next time we will continue with transistor family devices.